Hello and welcome to this extension topic clip on hydrogen emission spectra. We're going to look at how atoms emit light if subjected to the right amount of energy, and how this links to the light given out by chemical reactions involving hydrogen in stars in the universe. It also provides direct evidence, alongside obviously measuring ionization energy using a mass spectrometer, for the orbital and energy level model of atomic structure. So if we represent a hydrogen atom, basically you've got a proton at the nucleus and an electron around it. That electron happens to exist in the 1s orbital. That's in quantum number 1, energy level 1. So let's assume that the electron is now struck by a photon coming from outside, a photon being a packet of energy. So within the visible spectrum of light you have red, orange, yellow, green, blue, indigo, violet. So let's say we have a photon that possesses energy equal to orange light, or if energy hits that electron, the energy has the same value as that possessed by a photon of orange light within the visible spectrum. That would, for example, cause the electron to become excited and push it up into the next energy level. So it's now in n equals 2, or quantum number 2. So it's moved up into the second shell. So in other words, because the energy that's provided exactly matches the energy difference between the two energy levels, the electron jumps to the second one. If it was slightly less or slightly more, it wouldn't do so. So the electron now drops back down to its ground state from its excited state. The ground state is where it normally resides in 1s, and the excited state was in energy level 2, or n equals 2. So as the electron returns to its ground state, it gives out a photon of precisely the same energy as the energy possessed by the photon it originally received a split second ago. So this photon is then picked up as light. So we used orange for the sake of argument. So the exact colour seen would depend on the energy possessed by the photon which struck the electron in the first place. So looking at violet light, for example, it has more energy than orange light. That means its frequency is higher, but its wavelength is shorter. So a violet photon may cause the electron to be promoted to an even higher energy excited state. And as it drops back down to the original ground state of 1s, it would give off a violet photon. So depending on the exact amount of energy, if it happens to match one of the energy differences, you'll get a coloured light given out. So this piece of apparatus is called a cathode ray tube. It's similar in a way to the old style television tubes, not the flat screen versions of nowadays, but we're talking 30 years ago or so. So if we put a sample of pure hydrogen in a sealed glass tube, and we apply voltage, then provided the hydrogen gas is at low pressure, some of the hydrogen atoms within the H2 molecules will have the electrons move up to their excited state from their ground state and back down again. As they drop back down into the ground state, these electrons may give off light, and this may be picked up as a faint glow. So this is another way of writing it. H in brackets n to n greater than 1, going to h n equals 1 plus hv. So the hydrogen electron in its excited state drops back down to the hydrogen electron in its ground state, and in doing so gives off light energy. So in reality, very few hydrogen atoms will do this at room temperature. You may only get a very faint glow, if at all, if you actually do this in the lab, but this happens to a much greater extent obviously inside the hot cores of stars. So hence they're light travelling many billions of miles, so we can actually observe it. But it doesn't take away from the fact that it can happen. And if the energy striking an electron in a hydrogen atom actually happens to match the energy difference between one energy level and another, then you will get the electron going from a ground state to an excited state, and then back down again, giving off light. So it's important to remember that not all photons can be seen. Light's often misunderstood. It's really just part of the greater electromagnetic spectrum. So if a substance is colourless, for example, it means the electrons in that substance's atoms may be giving out photons just like we've talked about, but those photons would be outside the visible light range, or their energy would be outside the visible light range. It doesn't mean that electron excitation isn't happening. So hydrogen emission spectra can be actually classified into different lines that you'll see. Some of these are listed at the bottom of the screen. So each one of these will occur at a different place within the visible spectrum. They're only one of a number of different series of lines that you'll see if you subject hydrogen to different ranges of energy. Some of them actually correspond to specific frequencies, like the Lyman series. And as you can see on the energy levels diagram, the difference in energy between higher energy levels is quite low, as opposed to the difference in energy between lower energy levels. So the Lyman series requires more energy to show itself, because it's a bigger energy drop, so therefore it takes more energy to promote the electron up to n equals 3 in the first place. The Paschen series takes place between 4 and 3, so it's quite high. Now, it's high in the sense that it occurs at high energy levels, but the actual transition from n equals 3 to n equals 4 and back down again doesn't actually require much energy, because the energy difference is quite low. So it's the energy difference we're talking about here. So all of these represent what we call spectral lines. So each series will give you a series of lines when you do an atomic emission spectrum, which we'll look at in a second. So I'll start by just quickly taking you through the technique that's used. We don't use a cathode ray tube anymore. We use something called an atomic emission spectrometer. The cathode ray tube has been around for over 100 years, and it's fairly limited in what it can give us. So let's say we wanted to go for the Lyman series. You take a stream of hydrogen gas, and that would be pure hydrogen gas. It wouldn't be hydrogen mixed with air. And you'd put it into a sealed atomization chamber in the spectrometer. The hydrogen molecules would be atomized. They'd be subjected to a very hot plasma flame. These can be up to 3,000 to 5,000 degrees centigrade, so very hot indeed. The hydrogen atoms that you produce as a result are then subjected to ultraviolet light to obtain your Lyman spectrum, and a range of spectral lines are observed and recorded. So I put a diagram of the energy levels within an atom, and what I'll try and do is explain what happens when you get the drop from the electron in its excited state back down to its ground state. So each downward pointing arrow represents the transition of an electron from its excited state back down to its ground state at n equals 1. So notice how as the transitions increase in their energy difference, they also become closer in frequency, frequency being the x-axis, for want of a better way of describing it. So this means the higher energy transitions are closer in energy to each other than the lower energy ones. So this convergence effect means that all the lines will have the same frequency at n equals affinity. And this is actually equal to the first ionization energy of hydrogen at 1,310 kilojoules per mole to the minus 1. Meaning that if this amount of energy is supplied as ultraviolet light, all the atoms in the sample will be ionized. So let's have a look at what's going on with this n equals infinity, this convergence. and how it actually links to the first ionization energy of hydrogen. So coming back to the energy difference as explained above, that's each of these arrows. So I'm just going to highlight them very quickly for you. So I'm talking about each of these changes here. It can be expressed as delta E equals hv. So the h stands for Planck's constant, and the frequency of the photon is shown by v. So if we multiply this by Avogadro's constant and multiply this by the frequency at which a convergence occurs, this particular expression then equals minus 1310 kilojoules. So at this point, if this particular amount of energy is applied to 1 mole of atomized hydrogen gas, what will happen is that the first ionization energy will actually be reached, and therefore all the atoms in the sample of gas will be ionized fully. So now let's have a look at some questions that could be asked about this kind of thing. Obviously they're not A-level questions, they'd be extension questions, but still it pays to have a little look at how they might ask you about this. So the first question asks us to draw a labeled diagram of a hydrogen discharge tube. That's exactly what we looked at earlier. So like we said, the instrument we needed is the atomic emission spectrometer. So next it says, describe the appearance of the visible part of the hydrogen spectrum. So there's a series of lines that you'd observe which converge and get closer together as their frequencies increase. So the next part asks to explain why the hydrogen spectrum provides evidence for the existence of fixed energy levels for electrons and atoms. So you need to move the page down a bit for this. And it's 4 marks, so there's a series of things we obviously need to say. So the first thing is the idea that each line represents a transition of an electron from its excited state, wherever that happens to be in the quantum levels, to its ground state at quantum level number 1. And in doing so it releases a fixed amount of energy which corresponds to a specific photon's frequency, which is itself a fixed value. The next question asks us what is meant by convergence. And this is to do with the frequency increasing, and therefore as that happens the lines representing delta E, or the drop from excited state to ground state, get closer together. So in which direction is there convergence? It's as the frequency increases and the wavelength decreases. So it asks us to explain why convergence occurs in the direction that you've stated. So as the frequency increases, delta E also goes up. So therefore the energy difference increases. But at the higher energy levels, the differences between them reduces. So the difference between energy level 3 and 4 perhaps is not as big as the difference in energy level between 1 and 2. This makes the lines appear closer together on the spectrum. So moving on to the next part of the set of questions. It says the complete hydrogen spectrum comprises more than just the Balmer series. There's also the Lyman series, which this clip has looked at a little bit more in detail, and the Paschen series, which we've also mentioned. It asks you to state how these series arise and explain why they occur in the ultraviolet and infrared regions respectively. So we've already said that the Lyman series is transitions back down to n equals 1 from n equals greater than 1. So n equals 2 down to n equals 1, n equals 3 down to n equals 1, n equals 4 down to n equals 1, etc. So because we said that delta E is high, it matches relatively high energy of the UV light. So to get the electron to go up to that much higher energy level and then drop back down, it would require higher energy or higher frequency photons, and they would match UV light. The Paschen series is in infrared. So this time the Paschen series is a transition into n equals 3. So delta E is lower between higher energy levels, so lower energy infrared is sufficient to achieve this. The next question asks us to connect the ionization energy of hydrogen and the radiation emitted at the series limit. So the IE, first IE, is released when the energy difference between n equals 1, so the ground state, and n equals infinity, so So the maximum amount of radiation permissible within the Lyman series is actually achieved. So moving the page down a little bit, the final part says, given the wavelength or frequency of radiation at the series limit, you need to name two constants which you'd require in order to calculate the ionization energy of hydrogen. Now this came from two particular parts of the expression we looked at a couple of slides ago. So our two constants are the Avogadro constant and Planck's constant. And I've drawn over the other two in blue so you can see them labelled separately. So the first ionization energy of hydrogen would be delta E, and the frequency at the series limit of the Lyman series would be H. So hopefully you found this a reasonably useful introduction into hydrogen emission spectra. Obviously you have emission spectra for other atoms as well. So I thought we'd just have a quick look at hydrogen because it's one of the more closely studied ones perhaps. It has obviously ramifications for astronomy, ramifications for quite a lot of quantum mechanics, quite a lot of the application of quantum mechanics to astronomy. So it's a very interesting area which you'd probably cover if you went on to do university chemistry. But in the meantime, thank you very much for your time, appreciate you listening, and hopefully see you soon.